This is Physics 104B, the Chapter 18 homework. Let's start with number 11. In a perfectly insulated container, 1 kilogram of water is stirred vigorously until its temperature rises by 7 Celsius degrees. How much work is done on the water? So the idea here is that we're going to do work, and that kinetic energy from the work we do gets put into raising the temperature. It asks how much work is done, so we need to find W equals what? We'll start with the first law of thermodynamics. Delta U equals Q plus W. Since it's a perfectly insulated container, there is no heat exchange, so Q is 0. We're left with delta U equals W equals mc delta T. So with that in mind, the work equals mass of the water times specific heat of the water times the change in temperature, and we get 29,000 joules. Number 13, a 40-watt heater or heat source is applied to a gas sample for 25 seconds, during which time the gas expands and does 750 joules of work on its surroundings. By how much does the internal energy of the gas change? We'll use the first law of thermodynamics. Delta U equals Q plus W. We'll first talk about Q, the heat. It's 40 watts, which is 40 joules per second, times 25 seconds. And then we take into account the work done. Now let's be very careful about plus or minus. It says the gas expands, and you learned in the lesson that an expanding gas is going to be doing negative, or there's going to be negative work, because the gas is doing work. Now we define W always in the first law of thermodynamics as work done to the gas. But if the gas is doing work to its environment, then W is negative. So we should have W equals negative 750 joules. So 40 watts times 25 seconds, 1,000 joules of heat put into it, minus 750 joules of work, and that becomes a net plus of 250 joules. And so by how much does the internal energy of the gas change? It goes up by 250 joules. Number 16, an ideal gas expands from the state P1V1 to the state P2V2, where P2 is twice P1 and V2 is twice V1. So it's going to expand, the volume is going to double, and the pressure is going to double. The expansion proceeds along the diagonal path AB given in the figure in the book, and I've drawn that on the page there. Find an expression for the work done by the gas during this process. All right, work done by the gas, remember, is negative of W because W is defined as work done to the gas. We should draw a picture here. And here I've drawn a doubling of pressure from P1 to P2 and a doubling of volume from V1 to V2. We need to draw the picture, so we see it makes this trapezoid right here. It goes from A to B in the expansion of the gas. And we can say that work done by the gas is this integral. Now work is negative of the integral of P dV, but we're doing the negative of W, so I'm doing the negative of the integral P dV, so that's why the negative sign is gone, and we'll come back to that one soon. If you look at, I need to figure out what exactly to put in for pressure. So let's make an algebraic equation based on finding what is pressure based on volume. We're going to need to look at the picture and think through this. So let's do this. We can say that pressure is whatever the slope of that line is times volume plus B. So we recognize it's a linear equation, slope times volume plus the y-intercept. And thinking back to how we did this back in Algebra 1, we need to find the slope. And so we can say M, the slope, is, and we're comparing between these 2 points, 2 times pressure 1 minus pressure 1, that's the y values, over 2 times V2 minus or 2 times v1 minus v1. That's the x values. So remember from Algebra 1, the slope is the difference of the y's over difference of the x's. And what we get is that the slope is just p1 over v1. Now continuing our algebra exercise here, that means that p is, and I'm substituting in the slope, p1 over v1 times v plus b. And we need to find the y-intercept. So b equals p minus p1 over v1v. And the y-intercept then becomes, if we simplify this, p1 minus p1 over v1 times v1. Well, the v1s go away. p1 minus p1 is 0. So we get that the y-intercept is 0. So what that means is we started, see where my pointer is, we started with this equation, p equals mv plus b, and we then brought it to p equals p1 over v1 times v plus b, and now we recognize b equals 0, so this becomes what I've got in the box here, that the pressure is p1 times v over v1. Well, all of that was necessary, getting this equation for p, so that we could plug it into the integral. So now we go back to what I've done in the black ink up here, the integral of p dv. Well, now we know what p is, so let's follow this arrow down here. The work done by the gas is the integral of, and I'm replacing p with p1 v over v1 times, dv. The constants p1 over v1 can get thrown to the outside of the integral, so we're taking the integral of v dv. And when we take that integral, it becomes 1/2 v squared, so the 1/2 gets thrown out of the integral. We're taking the integral of v squared. Remember the limits of integration, v1 to v2. And we know that v2 is 2v1, and so let's do that. So when you follow through this integration, it becomes p1 over 2v1 times 2v1 squared minus v1 squared. And that in the brackets becomes 3v1 squared, because it's 4 minus 1. And in the end, we get 3 halves p1 v1. That is the way to solve this problem using integration. There was a non-calculus way of solving it that's actually a bit easier. Use the area of a trapezoid. And so let's go back, look at this picture, the area of the trapezoid. And to think, what is the area of the trapezoid? It is 1/2. Let me back out of that. Let me say it another way. It is the average of the two heights times the base. So the average of the two heights times the base, that's going to be this p1 plus 2p1. There's the two heights, average them, divide by 2. And then times the length of the base, 2v1 minus v1. And that gives us 3 halves p1 v1. And then we should check whether this should be positive or negative, because that answer will only give us we've only found the area of the shape, which will always be positive. So we should check, is this really positive or negative? Well, if we read back to the problem, physically the solution is that the gas expands. And the question is asking, find an expression for the work done by the gas. And so yes, the gas will be doing positive work on its environment. Number 17, repeat that exercise. Now this one will go a bit easier. For a process that follows path ACB, and it's drawn in the book, but I've drawn it right here, ACB. Still going from, as question 61 was, from P1 V1 to P2 V2, but because of the rectangular nature of this, it'll actually be a bit easier. We have to think about the two different steps. And the first step is going from path A to C. That's the easy one. It's isochoric, otherwise known as isovolumetric. Because volume stays the same, there is no work done. That part goes to 0. Then we're going to add to that the work going from path C to path B. Now the work done by the gas is pressure times delta V. The work done to the gas is negative P delta V, but we want the work done by the gas, so it's positive P delta V. And so we make our substitutions. P is 2P1, so you can see that it happened at that higher pressure, which is twice P1, times the difference in the volumes, V2 minus V1, which is 2V1 minus V1, and it becomes 2P1V1. Number 18 says a balloon contains 0.3 moles of helium. It rises while maintaining a constant 300 Kelvin temperature to an altitude where its volume has expanded 5 times. Neglecting tension forces in the balloon, how much work is done by the helium during the isothermal expansion? So we look for keywords in there. It says a constant 300 Kelvin temperature, then it reminds us it's isothermal. Well, I've written out the given information. N is 0.30 moles. We have temperature 300 Kelvin. I iterate in parentheses isothermal just to remind myself of that. It tells me what equation I should use. And V2 is 5V1. Question is asking, what is the work done by the helium? If you look at your isothermal equation, W equals, in the book, negative nRT times the natural logarithm. But remember, that's W as defined as work done to the helium. This is work done by the helium, so we're going to get rid of that negative sign, take the opposite of the expression. nRT times the natural logarithm of V2 over V1. I plug in those values. We don't need to know explicitly what the volumes are, only that it's increased by a factor of 5. So in that logarithm expression, V2 becomes 5V1. The V1s divide out, and we're left with just taking the natural logarithm of 5. And we get plus 1204 joules, and since work is done by the helium, positive work is done, that means it expands. Next is number 36. An ideal gas expands to 10 times its original volume, maintaining a constant 440 Kelvin temperature. So very similar to the last problem, we have an expansion, we're given the ratio of the expansion, and we have a constant temperature that's given. If the gas does 3.3 kilojoules of work on its surroundings, how much heat does it absorb? And how many moles of gas are there? I've written out the given information, being careful to note that work is negative. Work done to the gas is negative 330 or 3,300 joules because the gas is doing 3,300 joules on its surroundings. We want to know what Q is. We want to know what N is. Let's use the first law of thermodynamics. Delta U equals Q plus W. Although since temperature doesn't change, delta U doesn't change. So U equals Q plus W. Therefore, Q equals negative W, and Q equals then positive 3,300 joules. So it absorbs 3,300 joules. Part B is asking about N. Well, we're going to use the isothermal equation. W equals negative nRT natural logarithm V2 over V1. We're solving for N, and it becomes negative of, and I've made a little mistake here. Let me correct it. I have left off that W is negative 3,300. So let me just put a negative sign in there. There we go. Negative of negative 3,300 joules, so those will cancel out, divided by R, which is 8.314. We have 440 Kelvin and the natural log of 10, which is the ratio of the volumes, and we get 0.39 moles. Number 38. A 0.25 mole sample of an ideal gas initially occupies 3.5 liters. If it takes 61 joules of work to compress the gas, so work in this case is going to be positive 61 joules, isothermally to 3 liters, what is the temperature? It's helpful to draw a PV diagram, so we see it's going from 3.5 liters to 3 liters isothermally. It's going to slide up the isotherm, and you can see the higher pressure. I've written out all the given information. Since it's isothermal, we're just going to invoke the isothermal work equation, solve it for T. So T is negative W over NR, natural log of V2 over V1. We're going to substitute in for V2, 3 liters, for V1, 3.5 liters, and we get 190 Kelvin. Number 40. It takes 1.5 kilojoules to compress a gas isothermally to half its original volume. How much work would it take to compress it by a factor of 22, starting from its original volume? Let's write out the given information. We recognize it's isothermal, so we're probably going to be using the isothermal work equation. We have that work is 1500 joules. And in that situation, we have V2 over V1 is 0.5. It's being compressed to half its original volume. And it wants, the question one is asking, V2 over V1 is 1 over 22. What is the work? Well, let's employ the isothermal work equation and see what we can come up with. W equals negative nRT times the natural logarithm. And if we do that, we can think about, let's get the changing quantities to the left and the constant quantities to the right. So W over the natural logarithm of the volumes equals negative nRT, which is constant. And that's what we're going to go on, the fact that W over the natural log of the ratio of the volumes is going to be constant based on how many moles there are and what the temperature is. So now I can set up this ratio, that the first work over the natural logarithm of the volumes equals the second work over the natural logarithm of the volumes. So 1500 joules over natural log of 1/2, which is the first case, is going to be equal to W over the natural log of 1 over 22. We're going to solve that for W and get 6.7 kilojoules. Number 43 says a gas sample undergoes the cyclic process ABCA, and I haven't drawn the picture, but the picture is drawn in the book, where AB is an isotherm. The pressure at A is 60 kilopascals. Find A, the pressure at point B, and B, the net work done on the gas. I've started by writing out all the given information. We have the pressure at A, 60 kilopascals. Pressure at B, we do not know. That's what question A is asking. We know the volume at A, because it's given in the picture as 5 liters, the volume at B is 1 liter. We know that AB is an isotherm, so as it travels around A and B, as it travels from A to B, we know that PV equals nRT, which is PV equals constant. So with that in mind, if PV is constant, we can say PAVA equals PBVB and solve for PB. When you plug in the values, you can keep the volumes in terms of liters. You don't have to convert those to cubic meters because we're only concerned about the ratio. 5 liters over 1 liters becomes 5 to 1. And we get the pressure at B is 300 kilopascals. Now for part B is asking, find the net work done on the gas. So we have to find the net work as it goes from A to B, then down from B to C, then back from C to A. Let's take those step by step. From A to B, it's isothermic. So we're going to use the isotherm equation. Work from A to B is negative nRT times the natural logarithm of those volumes. Now, we don't know N, we don't know T, but we do know, look back up here, that nRT is constant. That's what happens on an isotherm. And we know that it's equal to pressure times volume. So let's substitute in for nRT, pressure and volume. We can do PA and VA, or we can do PB and VB. It doesn't matter. I would prefer to stick with A, because if we do PB and VB, then if we messed up on pressure at B, we're going to mess up on this one. So let's use the given information, PA and VA. We have 60 kilopascals, which we're going to need to make that, well, we can make it 60,000, but you notice what I've done here. I've actually kept it. You can, if you want to, convert it to MKS units. I've just kept it as kilopascals and liters. So I have 60 kilopascals times 5 liters, and that's fine as long as you stay mindful of the units you're using, times the natural logarithm of 1/5, and it becomes 482.8, but we have to stay mindful of those units, kilopascals times liters. Now, the work done from B to C is 0 because there's no change in volume. The work done from C to A, it's that horizontal line where pressure stays the same and volume increases. That's just negative P delta V. So it's negative P of A times 5 liters minus 1 liter. I've kept it in terms of kilopascals times liters. So negative 60 kilopascals times that difference, which is 4 liters, negative 240 kilopascals liters. So the sum of all those works, the 482.8 plus the 0 plus the negative 240, is 243 kilopascals liters. Now's the point where, not having done those conversions to MKS, it's going to catch up to us. Well, the reason I didn't convert back then was, if you look at, there was the work from A to B, I would have had to do those conversions. And then the work from C to A, I would have had to have done those conversions. Now, I just have one conversion to do, so just a little easier. So 243 kilopascals liters is 243 pascals kiloliters. Now, a kiloliter, remember that 1,000 liters is a cubic meter. So a kiloliter is a cubic meter. That's convenient. But you look back and see what I did. Kilopascals liters, I just moved that kilo, because kilo really means times 1,000. So I moved it over from the pascals to the liters. Instead of being kilopascals liters, it's pascals kiloliters. Very convenient when you see that you can do that. So pascals kiloliters becomes pascals cubic meters, which is joules. So 243 joules, I'm going to round that to 240 joules. The next problem is number 58. There's a picture drawn in the book. I've approximated it on the screen. It shows data and a fit curve from an experimental measurement of the pressure volume curve for a human lung. Estimate the work involved in fully inflating the lung. And my hand-drawn picture is leaving out some details, but let's look at the important aspects of it. We can see I've drawn the limit, so the pressure goes from 0 to 1,600. I'm sorry, the volume is going from 0 to 1,600, and the pressure is going from about 0.5 to 35 kilopascals. Now, you notice, I want to avoid some confusion here, the picture in the book is drawn as volume with respect to pressure, as you can see what I've done here. But if we want to think about it as a PV diagram, remember PV is pressure on the vertical axis, volume on the horizontal axis. So I've actually rotated this graph so it fits the PV diagram that you're used to. Okay, now if we look at this, it looks approximately linear, not exactly, but this is an exercise in estimating. Estimate the work involved. And so it's roughly linear, linear trend will make this mathematically easy. We're looking at a trapezoid here, and we're going to find the area of the trapezoid as it goes from a volume of 0 to 1,600 milliliters. So the area of a trapezoid is 1/2 times the two different heights. So we're taking the average of the two heights times the base. I'm leaving it for now in kilopascals and milliliters. So when we do 1/2 times 0.5 plus 35 kilopascals times 1,600 milliliters, I get 28,400 kilopascals milliliters. Those are the units. Now, conveniently, kilo and milli divide each other out because kilo means times 1,000, milli means times 10 to the negative 3. Those divide out completely, and we're left with pascals, liters. Now, I want this in MKS units. I want joules. So liters, we need to turn that into cubic meters. Remember that a liter is 10 to the negative 3 cubic meters. And so we're going to multiply by 10 to the negative 3 cubic meters over liters, and we get 28 joules. Number 66 says an 8.5 kilogram rock at 0 degrees Celsius is dropped into a well-insulated vat containing a mixture of ice and water at 0 degrees Celsius. When equilibrium is reached, there are 6.3 grams less of ice. From what height was the rock dropped? What's going to happen here is that for the most part, everything's going to stay at 0 degrees Celsius. We're dropping the rock. It starts with this potential energy. It gains kinetic energy. And when it hits the icy water mixture, all of its energy is going to get put into heating up or giving heat to the ice. And the ice is going to, it's going to change, it's going to melt. And we're not going to worry about anything changing temperature. We're just going to have the rock start at 0 degrees. And so the ice is 0 degrees, the water is 0 degrees. The water's temperature isn't going to go up because all of the energy is going to get put into melting the ice. So we're not going to worry anything about any changes in temperature. And we're dealing with 6.3 grams of ice that got melted. So right here where my pointer is, you can see the potential energy of the rock becomes kinetic energy of the rock, which becomes the heat of melting the ice. So let's think about potential energy of a rock that is up at a high height. Well, that's the rock's mass, so m sub r times g times h. And conservation of energy says all that energy will become the heat that goes into melting the ice, and that's the mass of the ice times heat of fusion. So we solve for height. Height equals mass of the ice times heat of fusion of ice divided by mass of the rock and g. Be mindful of that we were given the ice in grams and the rock in kilograms. So I'm going to call that mass of the ice 0.0063 kilograms. Heat of fusion 334,000 joules per kilogram. Mass of the rock, g, 9.8 meters per second squared, and we get a height of about 25 meters. While question 58 dealt with pressure-volume relationship in a human lung, we now go to number 68. It says experimental studies show that the PV curve for a frog's lung can be approximated by pressure equals 10V cubed minus 67V squared plus 220V, with V in milliliters and P in pascals. Find the work done when such a lung inflates from 0 to 4.5 milliliters volume. I've given the equation as it's given right there. We want to find the work done, so work equals negative of the integral PdV with those limits of integration. And we're going to inflate the lung from 0 to 4.5 milliliters, so there's the limits of integration. We're going to take this integral. Take the integral, so 10 fourths v to the fourth minus 67 thirds v cubed plus 220 over 2v squared, and of course the negative sign before the integral. Taking from 0 to 4.5 milliliters. Be careful of units. They were given in pascals and milliliters. And so what we have is 1218 pascals milliliters. But let's get that in MKS units. Well, pascals are already MKS, but let's deal with those milliliters. 10 to the negative 3 liters equals a milliliter. And then 10 to the negative third meters cubed equals a liter. So those liters will divide out. Milliliters will divide out. We're left with meters cubed. And we're left with 1218 times 10 to the negative 6 joules, or 1.2 millijoules. And if you go back and look at number 58 for the human lung, it came out to be about 28 joules. So much more work it takes to inflate a human lung. That's the end of the chapter 18 homework. Have a great day.